If we turn to the next page, we see these series of ray diagrams. And this is to be a human eye. And here's the retina. So there's our focus. First thing you're going to do is take a ruler and measure the focal length of this lens. Now on screen, I can do it this way. And it says 22 millimeters. So I have a focal length of 22 millimeters on this single lens. I'll put that here. Further down, you look at where the focuses are. This lens has a longer focal length. So you take a ruler, you measure the focal length, and you get 31 millimeters. Now, I don't care if you get 31, 30. Like, seriously, it's not that important. It's the technique, not actually getting the numbers. Getting the numbers to multiple decimal places, that's important when you're building lenses. You can be certain that your camera, they probably took it to like 6 decimal places. So what we want to see is what happens when we put our two pretend objects and ray trace them on the short focal length lens. If the lens has a short focal length, it projects the image right here on the retina. I set it up to do that. The retina in this lens is located approximately 2 focal lengths back, about 49 millimeters. So that's where this person is seeing. Now, with the same focal length, which your eye does not do. Your eye is supposed to change its focal length, but sometimes it can't. So the thing you're watching moves further away. And what do we see happening? The focus is moved to here. So if I grab myself a little arrow, draw myself a little arrow here, I'll have to rotate him like this. Yep, still in rotate mode. I've got a focus right there. So basically, my image is now a really little tiny one right here. The fact that the image has gotten smaller is okay. As people get further away from you, the image shrinks. But unfortunately, the focus or the formation of the image is now significantly in front of the retina. And this means the 3 rays that came together to make the image right here, by the time they reach the retina, they have scattered. And what does that mean? It means this. There's an image there. There's an image there. There's an image here. That's called the blur. You're not going to see anything there. So this lens sees best when the person is near or far from their target. The 22 millimeter focal length lens of this person's eye sees perfectly when the object is close. But as the object moves far away, the image starts forming in front of the retina.
Just a reminder, there is a yearbook meeting in 609, yearbook meeting in room 609.
This means you're farsighted. Or does it mean you're nearsighted? I almost tripped myself up. You see well when it's near. You don't see well when it's far. So you're nearsighted in this one. What happens when we switch cases to the 31 millimeter lens? On the 31 millimeter lens, we have a problem that our image is forming way out here. Way out here somewhere, there's a monstrous image coming together. Out here somewhere. I didn't extend my lines to where they meet. My eyesight, that seems to me where they're heading. So they're on their way, but they haven't closed yet. So again, the light from the tip must show up in one spot on your retina for you to recognize it. Instead, the light from the tip is landing at 3 separate locations on your retina. That's called a blur. But on this longer focal length lens, because there's a greater distance between the center and the focus, when the thing you're looking at moves farther away to this position, suddenly the image is on the focus. Or sorry, it's focusing together on the retina. So does this person with a long focal length eye see better when the object is up close and the image is here? Or do they see sharply when the image is back here, the object is back here, and the image is here? This person sees best when the object is far away. So this person is farsighted. Most of us, through most of our lives, our lenses will adjust the focal length. So in reality, what your eye may do is squish the lens. When your friend starts at a great distance from you, your lens will relax and have less curvature, causing the focus to move out and allowing you to focus on faraway objects. As your friend walks closer to you, to avoid this happening, the lens relaxes and, the lens contracts to bend the light in to a shorter focal length. So your lens is a smaller circle now than before. So a long focal length lens will have a shape like this. And as the focal length shortens, right, the lens will pull in like that. So long focal length, focus will be way the heck out of here. And short focal length, bend the glass more and it will bring the focus in. So your lens should change its shape and do an adaptive focal length to get the better focus. Camera lenses don't. How a camera lens would get the focus is literally the sensor moves back and forth. So when you focus your camera, it goes back and forth. Or instead of moving the sensor, the lens moves. And the lens goes back and forth when you focus, and you can refocus like that. Human eyes don't do that. They would look really strange if they bulged in and out of our head. So this is how you can determine which one sees better at a different range.